Time travel has long fascinated both scientists and dreamers, inspiring theories that dance between the edges of physics and philosophy. Within the framework of quantum physics, the idea of moving through time gains peculiar, sometimes paradoxical possibilities. Unlike classical physics, where time is an immutable arrow flowing forward, quantum theory introduces elements of uncertainty, entanglement, and non-locality that challenge our everyday understanding of cause and effect. At the heart of quantum physics lies the concept of superposition, the ability of particles to exist in multiple states simultaneously. In this strange domain, events do not always unfold in a single, linear sequence. A particle might take several paths at once, existing in all of them until observed. This phenomenon has led researchers to question whether time itself could be treated as a quantum variable, one not strictly bound to a forward progression. Entanglement, another cornerstone of quantum mechanics, links particles across vast distances, allowing them to influence each other instantaneously. Some interpretations suggest that entanglement could transcend spatial separation and potentially even temporal separation. This opens the door, at least theoretically, to the idea of communicating or correlating events across different points in time. Quantum tunneling also contributes to this discussion. It allows particles to jump through barriers they shouldn't classically pass, seemingly defying time-bound logic. In rare conditions, the mathematics behind tunneling implies that effects can precede their causes, introducing retrocausality, a concept where the future influences the past. While not yet proven in a way that allows macroscopic time travel, it adds fuel to the theoretical fire. Physicists have also considered whether closed timelike curves, CTCs, hypothetical loops in spacetime allowed by certain solutions to Einstein's field equations, could exist at the quantum level. These would allow particles to loop back and interact with their former selves. Though highly speculative, some quantum models allow for CTCs without leading to paradoxes, thanks to the probabilistic nature of quantum measurements. In these models, the universe self-consistently avoids contradictions. Efforts to unify quantum mechanics with general relativity often lead to strange temporal behaviors. In quantum gravity scenarios, such as those proposed by loop quantum gravity or string theory, time may not be fundamental at all. Instead, it might emerge from more primitive, timeless structures, suggesting that what we experience as the flow of time is a macroscopic illusion, a statistical property of entangled quantum states. This emergent perspective hints that time could be manipulated under the right conditions, given sufficient control over the quantum fabric of reality. Quantum experiments with delayed choice and quantum erasers also suggest that actions performed in the present can alter the outcomes of measurements made in the past, depending on the interpretation. These effects don't allow for time travel in the science fiction sense but demonstrate that the quantum world doesn't obey the classical sequence of before and after. Reality, it seems, waits to decide what happened until it's asked. Some researchers speculate that if the universe is a quantum computer at its core, then rewriting the code might allow for retroactive changes in state, akin to editing the past. Others consider that quantum time travel could be possible inside black holes or wormholes, where extreme warping of spacetime could twist causal relationships. Though these scenarios remain deeply theoretical and beyond current technological reach, they point to a tantalizing possibility, that time may not be a one-way street, and the keys to traversing it might lie hidden in the subatomic shadows. Some of the most compelling scientific approaches to quantum time travel stem from attempts to reconcile general relativity with quantum mechanics, a goal that remains elusive. In general relativity, time is treated as a dimension woven into the fabric of spacetime, curved and stretched by mass and energy. Solutions like the Gödel metric in Kerr black holes allow for closed timelike curves, CTCs, mathematical pathways that loop back in time. However, these are solutions to the classical Einstein field equations. When quantum effects are introduced, things become more nuanced. In quantum field theory, the vacuum is not empty but teems with fluctuations, virtual particles that pop into and out of existence. These quantum fluctuations respect the uncertainty principle, where precise measurements of time and energy cannot coexist. According to Heisenberg's relation delta E, delta t greater than or equal to /2, extremely short time intervals allow for large energy uncertainties. This introduces the possibility that quantum fluctuations might, under specific boundary conditions, briefly distort spacetime in a way that permits causal anomalies, tiny, fleeting, localized bubbles where information could loop. One of the most intriguing theoretical models is David Deutsch's approach to quantum closed timelike curves. In his 1991 proposal, Deutsch used the framework of quantum computation to analyze what happens when a qubit travels along a closed timelike curve and interacts with its past self. His solution avoids logical contradictions like the grandfather paradox by invoking the fixed-point theorem of quantum operations. The idea is that the system evolves into a self-consistent state, one that solves the time loop without violating the unitarity of quantum mechanics. This gives rise to a type of many-worlds consistency, where all interactions, even backwards in time, obey the rules of probability and coherence. Furthermore, in path integral formulations of quantum mechanics, originally proposed by Richard Feynman, the probability amplitude for a particle's journey is calculated by summing over all possible histories between 2 points. Some physicists, like Yakir Aharonov and collaborators, have extended this framework into the two-state vector formalism, TSVF, where the quantum state is defined not just by initial conditions, past, but also by final boundary conditions, future. In this time-symmetric approach, particles are described by a pair of wave functions, one evolving forward in time and another backward. This retrocausal formalism implies that future measurements can influence past states, not in a way that enables messaging into the past, but in a way that may reflect deeper symmetries in quantum reality. Another deeply technical line of investigation involves quantum information theory. In particular, the no-cloning theorem and the quantum teleportation protocol raise questions about the temporal structure of entanglement. Quantum teleportation requires a pre-shared entangled state and classical communication, which obeys relativistic causality. However, some proposed modifications involving post-selection, a controversial technique where only desired outcomes are kept, enable simulations of causality violations in laboratory conditions. For instance, Seth Lloyd and colleagues proposed a model using post-selected quantum teleportation that mimics time travel effects without real temporal displacement. In loop quantum gravity, time may not be fundamental. The theory treats spacetime as quantized at the Planck scale, 10 superscript 3m, where geometric quantities like area and volume come in discrete chunks. Here, the smooth flow of time breaks down into a probabilistic evolution of spin networks, combinatorial graphs that represent the quantum geometry of space. In this regime, time could be an emergent property of entanglement between subsystems rather than a background parameter. This aligns with recent proposals from quantum cosmology that treat the universe's wave function as timeless, evolving only in relation to internal clocks, subsystems within the universe used as references. In string theory, especially in the context of AD/CFT duality, time is encoded in boundary conditions of a lower-dimensional conformal field theory. The holographic principle suggests that our experience of time within a higher-dimensional bulk emerges from more fundamental, static configurations at the boundary. In some formulations, the bulk time corresponds to renormalization group flow in the boundary theory, again implying that what we call time might be a derived quantity. If so, manipulating the boundary conditions or entanglement structure of the universe's information content could, in principle, enable modifications to how time is experienced or traversed. Temporal entanglement, though less well-known than spatial entanglement, is an area of growing interest. In standard quantum entanglement, two particles share a state across space, so that measurements on one immediately influence the other. But in certain protocols, such as entanglement swapping and delayed choice experiments, correlations arise between particles that never coexist in time. This leads to the startling possibility that entanglement itself is not constrained to simultaneity. Some theorists suggest that temporal entanglement could allow information to be braided through time in a way that defies classical sequencing. One of the most compelling experimental setups is the delayed choice quantum eraser. In this experiment, decisions made in the present determine whether interference patterns appear for photons that have already been detected, suggesting that quantum behavior is not finalized until measurement contexts are known, even retroactively. While this doesn't permit controllable signaling into the past, it highlights the malleability of temporal ordering in quantum events. It is as if quantum systems possess a holistic memory of all potential configurations, past and future, and only collapse once the full informational context is established. In 2020, a team led by Kaslov Bruckner at the University of Vienna explored scenarios where the causal order between events becomes indefinite. In so-called causally non-separable quantum processes, the question of which event causes which becomes meaningless. Both a causes B and B causes A coexist in superposition. Using quantum switches, where operations occur in a superposed sequence, they demonstrated that such acausal processes are not only mathematically consistent but also potentially useful for quantum computation. This raises the radical idea that time might not always flow in a fixed sequence, and under certain quantum regimes, causality itself becomes a dynamic, fluctuating entity. Theoretical proposals involving wormholes also touch on quantum time travel. In particular, the ER equals EPR conjecture, proposed by Meldesena and Susskind, posits that entangled particles, EPR pairs, are connected by microscopic Einstein-Rosen bridges, ER, or wormholes. If true, this would unify entanglement and spacetime geometry, suggesting that information passing through entangled qubits is equivalent to traversing a non-traversable wormhole. Recent work by Daniel Jeffries and colleagues used quantum teleportation in a laboratory simulation of traversable wormholes via quantum circuits. While no actual wormholes were created, the experiment hinted at the possibility of manipulating spacetime-like information flows using entangled quantum states. Some researchers are pushing even further into quantum retrocausality. In these models, cause and effect are not rigidly separated by time, but rather by the flow of information. Experiments involving weak measurements, where a quantum system is probed gently enough to avoid full collapse, suggest that information about future measurement settings can influence the interpretation of past events. The past quantum state formalism, developed by Gammelmark, Julsgaard, and Malmer, treats the evolution of quantum systems as influenced by both pre- and post-selection, unifying the roles of initial and final conditions into a time-symmetric framework. In this light, the universe may behave like a quantum feedback system, one in which the future plays an active role in shaping the present. This is not traditional time travel, but it raises profound questions. If future boundary conditions can influence quantum histories, could they be engineered to nudge the past? Current experimental limitations, such as decoherence and the fragility of quantum states, prevent practical realization of these ideas. But the mathematical consistency of time-symmetric and retrocausal models invites a deeper look into whether time is a fundamental axis or an emergent phenomenon. The universe, viewed through this lens, is less like a line and more like a web, where strands of time are interwoven by quantum entanglement, and where travel might not involve moving through time, but shifting its structure. If we look ahead to the technological frontier, experimental physics is beginning to design setups that, while not time machines in the science fiction sense, test the very fabric of causality and temporal coherence. One of the leading areas is quantum computing, particularly the manipulation of qubits in systems that allow for time-reversible operations. Quantum gates, such as the Toffoli or Fredkin gate, are logically reversible. This property is critical because it allows circuits to be run forward and backward, a prerequisite for any controlled temporal manipulation. In 2019, a team at the Moscow Institute of Physics and Technology reported a remarkable quantum simulation using IBM's superconducting quantum computer. They constructed a system that effectively reversed the evolution of a quantum state, a highly delicate operation, only possible under extreme control and with very low probability. Although it wasn't actual time travel, it demonstrated that quantum states, in principle, can be evolved backward, undoing entropy for a single qubit under artificial conditions. While this reversal decayed exponentially with added qubits, the concept hints at how temporal asymmetry might be locally circumvented in quantum regimes. At the same time, work in quantum cosmology explores how time behaves at the edge of the universe, such as near the Big Bang or inside black holes, where classical general relativity breaks down. The Wheeler-DeWitt equation, a central equation in canonical quantum gravity, does not contain time as a parameter. Instead, it treats the universe as a static quantum wave function. This problem of time suggests that time may emerge only when an observer interacts with the system, a concept aligned with relational quantum mechanics, where all physical properties, including time, are relative to the observer. In some interpretations, notably Carlo Rovelli's relational quantum theory, time doesn't exist independently but emerges from correlations between systems. A clock is not a universal tick-tock but simply one quantum system whose evolution is compared to another. If this is true, then traveling through time may not require traversing a spacetime manifold but rather altering the network of quantum correlations. You don't move to the past, you reconstruct it via entangled observables and consistent histories. This leads to a provocative possibility. If we could manipulate the quantum state of a system and control its entanglement history with sufficient precision, we might be able to reconstruct the past, not merely simulate it, but retrieve aspects of it that are causally consistent with the present. This has philosophical consequences as well. Is the past gone, or is it preserved in the correlations of the quantum state of the universe? If so, time travel may not involve jumping into a DeLorean, but tuning into the right quantum frequency, like accessing a channel that is still broadcasting, just not visible without the right entangled receiver. Even more futuristic are theories involving quantum retrotransaction, as explored in the Transactional Interpretation of Quantum Mechanics by John Cramer. This interpretation proposes that quantum events involve an exchange of waves both forward and backward in time. An offer wave propagates forward, and a confirmation wave propagates backward. Only when both waves match does the quantum event become real. Though not widely accepted due to its exotic nature, this interpretation naturally accommodates temporal loops and causal feedback in a consistent, non-paradoxical manner. In theoretical frameworks that go beyond our standard quantum mechanics, such as non-Hermitian quantum theory, PT-symmetric systems, or post-quantum cryptographic protocols, the idea of modifying temporal behavior becomes a research playground. These advanced models allow for complex time evolution operators, where nonlinearities and hidden symmetries might, under specific conditions, make time behave like a controllable parameter rather than an absolute. So far, every approach remains bounded by the no-signaling theorem, which prohibits faster-than-light or backward-in-time communication in any known quantum system. However, just as flight was once forbidden by the physics of hot air, and lasers were once thought useless, the story of time travel may be one of discovering a deeper set of laws, where time is a programmable variable, not a rigid constraint. Venturing deeper into speculative physics, some of the most provocative ideas about quantum time travel emerge from multidimensional theories such as brane cosmology and the multiverse framework. In string theory and M-theory, our observable universe is envisioned as a three-dimensional brane floating in a higher dimensional bulk. These higher dimensions, beyond the familiar four of spacetime, could, under the right conditions, allow shortcuts between distant regions of space or even loops in time. In brane world scenarios, gravity is allowed to leak into the extra dimensions, which might offer a theoretical basis for constructing stable wormholes. If such a wormhole connects two regions of spacetime and one mouth experiences relativistic time dilation, say, by orbiting a black hole, then a time differential is introduced. Under exotic matter conditions that prevent the throat from collapsing, such a wormhole could, in principle, allow for traversal between two times. While this idea remains purely theoretical, it is grounded in legitimate extensions of general relativity and quantum field theory in higher dimensional spacetimes. Parallel to this, the many-worlds interpretation, MWI, of quantum mechanics offers an alternative route to time travel without paradoxes. According to MWI, every quantum event spawns a branching of the universe, each path corresponding to a different outcome. If time travel were possible, it would not allow one to alter the past of the traveler's own timeline, but instead cause them to arrive in a different, causally consistent branch. In this model, the so-called grandfather paradox is naturally resolved. Killing one's grandfather in the past simply causes the traveler to diverge into a parallel universe where that action occurred, while their original branch remains untouched. Hugh Everett's original formulation of MWI didn't address time travel directly, but recent theoretical explorations have begun to apply branching logic to hypothetical temporal displacement. Researchers have proposed quantum branching time machines that, instead of looping back within a single timeline, send the traveler into a version of the past within an alternative branch of the universal wave function. This view preserves causality and unitarity while allowing for a kind of one-way temporal displacement, not truly reversing time, but sidestepping it through the multiverse. In the context of holographic theories of the universe, particularly the AD/CFT correspondence, time may also be encoded as a boundary phenomenon. The correspondence proposes that a gravitational theory in a higher dimensional bulk is equivalent to a quantum field theory on a lower dimensional boundary. If time evolution in the bulk corresponds to renormalization group flows on the boundary, then reversing the boundary flow could imply a form of temporal inversion in the higher dimensional reality. Some physicists have speculated that this duality might be harnessed to manipulate the arrow of time, though the mathematics is still in its infancy. Meanwhile, researchers in quantum complexity theory are beginning to describe the universe not in terms of energy or entropy, but computational complexity. In this view, time flows in the direction of increasing complexity. A highly ordered quantum state, over time, becomes more scrambled as entanglement spreads. Reversing time would require reversing this scrambling, akin to unmixing a quantum soup. But if the universe is a quantum computer, as some theories suggest, then there might exist exotic algorithms that reduce complexity locally, perhaps offering a computational handle on the flow of time. This ties into the concept of quantum time crystals, structures that exhibit temporal periodicity in their ground state. First theorized by Frank Wilczek in 2012 and realized experimentally years later, time crystals do not move in space, but oscillate in time without energy input. While they don't permit time travel, their existence challenges the classical understanding that the lowest energy state must be static. In a broader view, such structures might one day be used to engineer materials where the passage of time is locally controllable or even repetitive, opening the door to quantum loops embedded in matter itself. Even more speculative are proposals involving closed timelike information loops in quantum neural networks, where quantum learning systems are trained on both past and future data simultaneously. In these hypothetical architectures, causality becomes bidirectional and adaptive. A sufficiently advanced system might converge on stable self-consistent timelines, correcting its own history retroactively to achieve optimized outcomes. The convergence of quantum mechanics, information theory, gravity, and high-dimensional topology suggests that time, as we experience it, is not a singular, absolute entity. It may be programmable, mutable, and deeply dependent on the observer's entanglement with the cosmos. Time travel, in this grand view, may not involve going anywhere, but restructuring the informational relationships between moments, as if editing a cosmic quantum script whose narrative is still being written. If time is ultimately a construct of information, then the future of time travel may lie not in exotic propulsion systems or cosmic gateways, but in our ability to manipulate the quantum state space of reality itself. One line of thought gaining traction in theoretical physics views the universe as a vast quantum error-correcting code. In this framework, space-time geometry, particle interactions, and even causality emerge from deeper principles of information encoding and redundancy. If time is a byproduct of how quantum information is organized and preserved, then rewriting or rerouting that information could, in principle, enable temporal navigation. This idea is bolstered by connections between black hole physics and quantum information. According to the holographic principle, the entire 3D volume of a black hole can be encoded on its 2D surface. Stephen Hawking's black hole information paradox, whether information falling into a black hole is lost or preserved, led to the discovery that black holes emit Hawking radiation and slowly evaporate, with quantum information somehow encoded in the radiation. If black holes are natural quantum scramblers that preserve temporal information in non-obvious ways, then studying them may offer keys to decoding and reconstructing the past. Recent developments in firewall and soft hair theories aim to explain how the quantum information of infalling matter is preserved. Some proposals even suggest that by collecting and analyzing the subtle quantum correlations in Hawking radiation, we could, in theory, reconstruct past events within the black hole's horizon, a form of time reversal via quantum information recovery. While this lies far beyond current technology, it reinforces a recurring theme: time may not be about moving a body backward, but about extracting or recomputing its earlier quantum description from the entangled state of the universe. Additionally, quantum gravity research is uncovering that the flow of time might be entropic, not fundamental. In the thermodynamic era of time, systems evolve from low entropy to high entropy, ice melts, stars burn, galaxies collapse. But entropy itself is a statistical measure of uncertainty. In a sufficiently fine-grained quantum description, the distinction between past and future could disappear. Indeed, in some quantum cosmology models, the Big Bang is not a singular starting point but a mirror of a big crunch, a time-symmetric structure where time flows away from the high-order center in both directions. This CPT-symmetric universe model, proposed by Neil Turok and colleagues, envisions a cosmos where our forward time is someone else's past. If such symmetry holds, then time travel may be built into the universe at a foundational level, not as a glitch or anomaly but as a reflection of the deeper time-neutral laws of physics. The apparent directionality we experience could be the result of boundary conditions, our specific region of spacetime, entropy gradients, and observational limitations. Future technologies might exploit these symmetries by creating regions of reverse temporal boundary conditions, localized bubbles where time flows differently, or even stably loops. Time travel through quantum mechanics also intersects with ideas from quantum biology and consciousness. Some speculative models suggest that consciousness may play an active role in collapsing the wave function, not just passively observing reality, but actively selecting it. If observer participation affects not just the present but retroactively influences the past, a notion hinted at in delayed choice experiments, then conscious agents could, under certain interpretations, be entangled with the temporal structure of the universe itself. Though highly controversial, this introduces a philosophical dimension to quantum time travel. The traveler may not be a mere passenger but a participant in the rewriting of time. As we refine our understanding of quantum decoherence, non-locality, and entanglement entropy, new possibilities emerge. Quantum teleportation of states, not matter, is already demonstrable over hundreds of kilometers, and quantum memories can now store entangled photons for extended periods. If future quantum networks evolve to the point where entire quantum states of macroscopic systems, including their temporal metadata, can be stored, transmitted, and reconstructed, then we may begin to approach a form of quantum resurrection, restoring past configurations in the present. Not movement through time, but reinstantiation of time. From quantum loops and boundary conditions to retrocausal waves and information-theoretic time, the conclusion becomes unavoidable: time is not what we once thought it was. And if time is malleable, then travel through it, while still a monumental challenge, may one day shift from fantasy to feasible, not by brute force, but by mastering the quantum code of the cosmos. One of the most tantalizing implications of time as an emergent quantum phenomenon is the idea that chronology itself, what we call the before and after of events, may depend entirely on the observer's frame of reference, not just spatially, as in relativity, but informationally. In certain quantum frameworks, two observers entangled with different subsystems of the same global wave function may disagree about the sequence of events without violating any physical laws. This leads to the concept of quantum causal relativity, where causality is not an absolute scaffold, but a flexible fabric shaped by correlations. Such models have been formalized using process matrices and indefinite causal order, tools that break free from the classical assumption that events must follow a strict temporal sequence. In this approach, events A and B may influence each other without any global agreement on which came first. Quantum experiments using photonic interferometers have already shown early empirical hints of such phenomena. This suggests that the causal structure of reality is not just subject to relativity of motion, as Einstein showed, but also to relativity of information access, a fundamentally quantum concept. These insights are finding a natural home in the growing field of quantum foundations, where researchers aim to redefine what events, histories, and even existence mean in a quantum universe. Some researchers, such as Lucian Hardy and Giulio Cirabella, are constructing operational probabilistic theories in which time is treated as a relational variable, and even logic itself can become non-classical when applied to temporal events. This introduces new logical frameworks, quantum temporal logics, where statements like event A happened before event B become context-dependent propositions, rather than universal truths. In this emerging logic, time travel could be thought of not as a traversal through a static fourth dimension, but as a reprogramming of the constraints that define temporal ordering in a given quantum network. This is akin to how classical data can be reordered or rewritten in memory, except the memory, in this case, is the universe itself. Looking even further ahead, theories that incorporate quantum gravity, especially those involving spin foams, causal sets, or group field theory, suggest that spacetime might be composed of discrete, pre-geometric units that do not possess any inherent notion of time or space. Instead, these quantum elements, or atoms of spacetime, interact through combinatorial rules that give rise to emergent geometry and causal structure. In such models, time is literally born out of the way information flows between events. One key insight here is that entanglement may be more fundamental than geometry. Spacetime might not be the background on which entanglement happens, but the product of it. This is supported by results from ADS/CFT, where the connectivity of space correlates directly with the degree of entanglement between regions. If time too is born from entanglement, then manipulating entangled connections could give rise to synthetic temporal pathways, entirely new causal structures engineered by quantum coherence. In more speculative corners, researchers have proposed using these principles to construct quantum chronotopes, regions of spacetime with engineered causal topologies. In theory, a chronotope might host closed temporal loops, delayed feedback between events, or even bidirectional causal flows. Within such constructs, time travel could manifest not as a journey but as topological re-entry into earlier quantum states, preserved in a non-classical causal lattice. To achieve such a feat, future quantum engineers might need to master quantum spacetime surgery, the ability to stitch, redirect, or excise portions of the causal fabric itself. Tools for this may come from quantum topology, braid theory, or categorical quantum mechanics, fields already being used to model non-classical paths and reversible computation. In such a universe, time travel is not breaking the rules of physics, it is playing a more advanced game, where time is a strategy rather than a law. All these directions converge on a profound realization: the universe is not a static block of spacetime, nor a pre-written script of causality. It is a living computation, constantly evolving through quantum states, where past and future may not be fixed addresses, but accessible configurations in a vast informational landscape. If time is not a fixed dimension but a fluid informational construct, then the classical paradoxes associated with time travel, like the grandfather paradox or the bootstrap paradox, must be re-evaluated under the lens of quantum logic and consistency. In classical terms, these paradoxes represent logical impossibilities. Changing the past would negate the cause of the change. But in quantum mechanics, consistency is enforced not through linear determinism, but through global coherence. This is the foundation of David Deutsch's self-consistency condition for quantum time travel. In his model, a quantum system entering a closed timelike curve, CTC, must evolve in such a way that the outcome is logically consistent with its own past. No contradictions can arise, not because they are forbidden by logic, but because the quantum evolution simply has no solution if a contradiction would occur. As a result, paradoxical scenarios, like killing one's grandfather, collapse into zero probability outcomes. The universe chooses only those paths that are globally self-consistent. This means time travel might be allowed in principle, but only in ways that preserve the overall logical integrity of the quantum wave function. The bootstrap paradox, where an object or piece of information has no origin, e.g. a time traveler gives Shakespeare a copy of Hamlet, and Shakespeare publishes it, also dissolves in quantum models. Such loops can be understood as fixed points in Hilbert space, where the information is distributed consistently across time, entangled between cause and effect. What seems like a logical loop in classical terms becomes a stable quantum eigenstate, a self-sustaining knot of information in spacetime. It exists not because it was created, but because it satisfies the boundary conditions of the entire quantum system. Furthermore, the observer's role in these processes becomes central. In quantum mechanics, the observer does not merely witness reality, they actively participate in defining it through measurement. If the timeline of the universe is not pre-written but co-authored by all observers embedded in it, then paradoxes lose their bite. The past isn't a fixed record, but a reconstructed narrative, consistent with all recorded interactions. Time travel, in this sense, would not allow rewriting the past, but realigning the system to a new quantum history that is still coherent within the multiverse. This leads naturally to the concept of quantum histories, as explored in the Consistent Histories interpretation of quantum mechanics, developed by Griffiths, Omnes, Gell-Mann, and Hartle. In this framework, a quantum system doesn't follow a single timeline but a superposition of many possible histories, each with a well-defined probability amplitude. The observer's measurements select a branch from this tree, not by collapsing it, but by entangling themselves with one consistent sequence. If histories can be probabilistically weighted, then, moving through time, might be reframed as reweighting or re-interfering with different history branches, again without contradiction. These ideas touch deeply on questions of free will, determinism, and memory. If the past is not fully fixed until observed, and if even then it depends on the context of present and future measurements, then memory itself might be part of the quantum entanglement web. Some speculative neuroscientific models propose that human memory and consciousness arise from quantum coherence in microtubules or other subneuronal structures, the Penrose-Hameroff orchestra model, for instance. While controversial, these models suggest that our perception of time could itself be a quantum process, giving rise to subjective flow from a fundamentally timeless substrate. In this view, time travel may not just be a technological challenge, it may require a redefinition of what it means to remember, to observe, to be. The line between temporal physics and metaphysics begins to blur. If the observer and the universe are entangled across time, then modifying the flow of one could alter the trajectory of the other. Not through mechanical means, but through informational alignment with different quantum configurations, worlds not back there, but encoded right now in the deeper structure of the wave function. In the end, the question of time travel through quantum physics is not merely one of machines and equations, it is a question about the nature of reality itself. The deeper we probe into the quantum fabric of the cosmos, the more we find that time is not a rigid track along which we move, but a delicate interplay of correlations, probabilities, and entanglements. Past and future may not be fixed destinations, but dynamic, reconfigurable layers of a timeless quantum field, waiting to be accessed not by force, but by understanding. Whether through closed timelike curves, entangled histories, or the emergent geometry of spacetime from quantum information, the possibilities are vast and strange. Time travel, if it is ever realized, may not resemble the fantastical voyages imagined in fiction. Instead, it might be a quiet recalibration of the universe's internal logic, a shift in the informational tapestry from which time itself emerges. Perhaps, in the quantum world, we never truly leave the past, nor are we fully bound to the present. We exist as part of a superposition of moments, each echoing through the wave function of the cosmos. To travel through time may not mean moving our bodies across eras, but learning how to tune into the frequencies of memory, possibility, and entanglement that already hold the past and future within them. And so, the true path to time travel may not be to conquer time, but to understand that we are already woven through it, in ways more profound and mysterious than we ever imagined.